Okay, last time we have discussed the absolute configuration of chiral molecules, and we have introduced to you the first system that was introduced earlier, and that was called the D and L, capital D and capital L system. This is a system to notify the absolute configuration. I again remind you what is absolute configuration. It is the absolute arrangement of the groups in the three-dimensional space. Okay. So, DL was the starting point. It was based on the carbohydrates, configuration of carbohydrates, which Professor Emil Fischer started. Okay. He assumed that plus glucose had the D configuration, that means the lowest possible chiral center, the hydroxy group is at the right, and that was he assumed to be D plus glucose, and it started then onwards. Now, the problem with this configuration, I just repeat what is this configuration, that if you have a chiral molecule and if you write it in the Fischer projection formula, that means the two-dimensional formula, and you should write it in a proper way, so that the carbon, there are two carbons suppose. So, the top one should be at the highest oxidation level, suppose it is between CO2H and CHO. So, the CO2H is a higher oxidation level than CHO. So, you put the CO2H at the top. Now, if you have a heteroatom on the right and a hydrogen on the left, we call this as the D isomer, capital D, and the opposite one where X is on the left and CO2H on the right, CHO at the bottom, then that will be called L. Remember, this is very important, the positioning of the carbon in the vertical axis, that actually decides whether your X will be on the right or on the left. Now, this system could not be applicable in case of where there is many cases. First, if there is no heteroatom, then what are you going to do? If there is no X, that means the heteroatom, then this will fall apart. If X is suppose methyl, then this will be replaced by a methyl that cannot be regarded as a heteroatom. So, sorry, not this one, this X should be replaced by methyl, but it is still chiral, but you cannot have a DL nomenclature system for this. Okay. So, it fails when X is an alkyl group, X is a different. I gave an example. The most important thing is X is not containing a heteroatom, and the other is that if there is no hydrogen, if hydrogen is missing, and if you have that is replaced by two heteroatoms, hydrogen is replaced by a heteroatom and X is already there. So, then there is a situation that you have two heteroatoms, maybe different, Y and Y here. So, both X and Y are heteroatoms. Then also the problem is which one is now which one I should get a preference, so that I can consider right or left. So, in these cases it fails, that means it is not a general absolute configuration. So, there must be some better way of looking at these molecules and name them accordingly. Okay. So, the next one was developed and was accepted by the International Union of Pure and Applied Chemistry. You know, the IUPAC is our organization which provides all the rules how to name a compound and then how to name a stereochemical compound. So, they accepted, they proposed whatever was the proposal by three scientists, very famous scientists. One is Kahn, another is Ingold, and the third one is Prelog. And sometimes this is called Kahn-Ingold CIP system. CIP system is nothing but Kahn-Ingold Prelog system. So, whatever they proposed, IUPAC has accepted, and it is a very general way of giving absolute configuration to a molecule. Now, what you do in this CIP system, suppose you have the carbon. Now, I am writing it in a tetrahedral fashion. You know that in the tetrahedral fashion, two bonds, all four bonds cannot be in the same plane. So, if one bond is up, then one bond has to be down, and these two bonds can be in plane. So, 3 bonds cannot be in a plane in a tetrahedron. There can be 3 bonds which are up, there can be 3 bonds which are down, 1 bond can be in the plane, but remember 3 bonds can never be in a plane in a tetrahedron. Okay. Now, this is a carbon which is a tetrahedron, and suppose this has got 4 ligands A, B, C. I just, in order to avoid carbon, I put D and E. So, if this is the scenario A, B, E, D, then what this IUPAC system, this RS system tells is that you assign a what is called a priority sequence of the groups of the ligands, priority sequence. Okay. And so, there must be a way to give priority to these atoms, and so the rules actually are 2 basically. First of all, after giving the priority sequence, how you should look at this molecule, and then you see that what are the sequence of priority when you go from 1 to 2 to 3. Okay. Let me clarify it a little better. Suppose by priority sequence rule, I will come to the priority sequence rule later. Suppose that this becomes number 1 carbon, and this becomes number 2 carbon, this becomes number 3 carbon, and this becomes number 4 carbon. Okay. So, this is 1, that is 2, that is 3, and that is 4. So, now the rule says that you should view this molecule in such a way that the number 4 carbon is away from you, away from the observer. So, here the number 4th carbon is actually behind this plane of the board. So, it is not difficult, the face that we are having here. So, we are actually in the front of the board, and this group which is the B group, which is having the 4th priority. So, the least priority, that is at the back. So, whatever I see from here, that is correct, that is according to the rule. The rule says you look at the carbon away from the 4th group. So, I am looking at the carbon away from the 4th group, and then you see what is the sequence order. If you go from 1 to 2 to 3, what is the direction order? What is the direction that if you go starting from 1 to 2 to 3, what is this order? Is it clockwise or this is anti-clockwise? So, in this case you can see that E 1, 2 and 3 are arranged in an anti-clockwise direction. Okay. So, in other systems, like if I draw the mirror image of this, suppose I draw the mirror image of the same molecule now. So, A will be now here, D will be now here, A will be here, B will be there, still alpha, this is a lateral image I am taking, and then D is here and E is there. Okay. So, these are the 2 systems that I get. Now, the priority sequence remain the same. So, 1 is here, then E was 2, 3 is D, and this is 4. This is 4. Now, if you look at this molecule, at this system, at the carbon, stereogenic carbon, again it's a you are following the CIP norms, that is you are observing the carbon away from the 4th group, because the 4th group now is behind the plane of the board. So, now you see what is the direction between if you go from 1 to 2 to 3 and back to 1. So, now you see this is clockwise, this is clockwise. So, this is what is called. Now, if this 1 to 2 to 3 direction is clockwise when you view a molecule away from the 4th group, then that will be called R molecule if it is clockwise. That actually has come from the Greek word rectus, means right, and anti, when this 1 to 2 to 3 direction is anti, when you observe the molecule, when you observe the carbon specifically away from the 4th ligand, the ligand of the least priority, and if the direction is anti-clockwise, then that will be called a S compound, and that is called sinister. Sinister is means left in Latin. Okay. These are Latin words, rectus and sinister. Okay. So, you know the, at least you know what to do in a if you have a 3-dimensional molecule, you have to assign priority sequence and then observe it from a direction. So, there are 2 things, assignment of priority, that is one important issue, and the second issue is the direction of view, which direction you should, from which direction you should see the stereogenic carbon. Okay. So, we have to now go to the sequence rules. How do we know that whether A is 1, whether B is 2 or B is 4, how do we know? So, what are the rules? Now, the rules say that your priority sequence, to assign priority sequence, you first check, use atomic number to distinguish between the ligands. Okay. So, what does it mean? That means, if a carbon has a fluorine and a chlorine, then chlorine has higher atomic number. So, chlorine will get better preference than fluorine. Okay. Now, the things may become more complicated later on, I will tell you, because the first atom that is attached to the stereogenic center may be the same, but the second atom may be different. That means, suppose this is CH2, then CH3 and CH3, and you have CH2 and then CH3. So, if you are asked to distinguish between these two, then what you do? You check the first carbon, first ligand which is attached to this stereogenic center, and you see what are the other ligands that are attached. So, what are the other ligands? One is carbon, another are 2 hydrogens. So, this is the scenario of this carbon. Okay. Here is also one carbon attached, hydrogen attached, another hydrogen attached for this carbon. So, there is no difference. So, now Kahn-Ingold-Prelog says that you continue proceeding towards the outerwards, towards the chain outerwards, away from the stereogenic center and then away from the stereogenic center, and then see where is the difference. Once you find a difference, you stop there and then assign the priority. So, first carbon did not do any, showed no difference. What about the second carbon? Here this is a carbon which is attached to 2 carbons and 1 hydrogen, and this is a carbon which is attached to 3 hydrogens. So, obviously, carbon being a higher atomic number atom. So, this one gets ultimately. So, this group wins over this one. So, this will be then we are discounting these groups. Suppose that means, this will get higher preference over this. This will be greater than this. Okay. So, if it is 1, then that is 2. Now, this type of work you have to continue in many cases. In many cases, you have to continue this going away from the stereogenic center to find a difference. Okay. Once you find a difference, then you stop and then assign the priority. Okay. So, what you use the atomic number as the criteria to do the discrimination. Once you are finished with the atomic number criteria and that still does not give any difference. So, it appears that the ligands may be same, no? But we are dealing with a chiral carbon. That will happen in case of in isotopic systems. Consider atomic weight to distinguish between the isotopes. Okay. So, to distinguish between the isotopes, but the rule now the important thing here is the number 1 rule has to be used first and then followed by the number 2 rule. Number 2 rule is atomic weight you use, here you use atomic number. Now, I will give you an example to stress this point. What I am saying that suppose if a deuterium is attached and a hydrogen is attached, and suppose a wedge and a methyl, then assigning priority sequence will be, this will be, if you go by atomic number, first you have to go by atomic number, So, atomic number wise this is number 1, then this is number 2, and then you are stuck. Atomic number cannot distinguish between deuterium and hydrogen, because both have same atomic number. So, now you have to use, once this rule cannot distinguish between the groups, then you distinguish these two, use your second criteria, that is the atomic weight criteria. So, based on the atomic weight criteria, this becomes 3 and that becomes 4. Okay. Another case may happen that you have CD2, then CH, CH3, CH3, and you have CH2, CH2OH. Okay. So, in this case, okay, this is one that is no longer 2 methyl, because this gets higher priority over this, because that is only attached to hydrogen, 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 no substitution. So, we write this. In case of this carbon, there is deuterium, deuterium and carbon. For this carbon, there is a carbon, there is a carbon, there is a hydrogen. Okay. For this carbon, there is hydrogen, hydrogen, carbon. For this carbon, there is hydrogen, hydrogen, oxygen. Okay. Now, according to the atomic number rule, this is number 1, then you apply the atomic number, continue atomic number until it falls apart, that it cannot distinguish. So, you see after this group there is hydrogen, hydrogen, carbon, there is deuterium, deuterium, carbon. But at this stage the rule 1 says that deuterium is equivalent to 1 hydrogen, because they have both atomic number. So, you have to use the atomic number rule first, and based on that this becomes, you cannot distinguish at this stage. Then you go to the next carbon and you see there is a difference, hydrogen, hydrogen, oxygen has come, atomic number more, here it is all carbon. So, which one is now number 2? So, this becomes number 2 and this becomes number 3 and methyl becomes number 4. So, you see, in spite of having the deuterium here, you could not give higher preference to this, because your first atomic number rule can distinguish between the two. First atomic number rule does not care whether there is isotopes, isotopes are regarded as the same. So, the atomic number rule, once that falls apart, then only you can utilize the isotope rule, that means the second distinguish between the isotopes. Okay. The third rule, this is the second rule. The third rule says that in case of a double bond, suppose you have a double bond attached to a stereogenic center, okay, and you have an isopropyl group. So, how the isopropyl group is compared with a vinyl group? This is called the vinyl group. So, what you do, it has been suggested that because there is a double bond present between these two carbons, so you think as if two extra carbons, one extra carbon is attached to this carbon and one extra carbon is attached to this carbon, because they are connected by a double bond. So, you have to break it into, so this is a stereogenic carbon, you have to break it into CH2, right, single bond, and then on both the carbons you attach an extra carbon. Why? Because this is attached to that by a double bond. So, it should have a double hand, 2 carbon atoms, and on the same argument this carbon is attached to this carbon by a double bond. So, now you have attached a single bond. So, you add another extra carbon. These are called phantom atoms, and in some books you will find, just to distinguish between the normal carbons, attached 0, but this has really no significance. They are behaving like the normal carbon. Only thing they do not have any substitution, that is the difference. Okay, let us continue. So, these are normal carbon, and then you have this isopropyl CH, CH3 and CH3. Now, let us see the first carbon you have, look at the first carbon, you have this is attached to the carbon, a hydrogen and a carbon, hydrogen and a carbon. This carbon is attached to a hydrogen, sorry, a CH2, this was CH2, sorry, this was CH2 CH3, CH3. Now, we better compare this one with, actually we continue with this HHC. The first one is HHC. Okay. The second one HHC. So, this wins over that one, because this is HHC and this is CCH. Okay. So, that has the higher preference than this. If we change it, suppose I change it to isopropyl. Earlier it was isobutyl. Okay. So, if I make it to isopropyl, then what will happen? This carbon is attached to what? Hydrogen, carbon, carbon. So, there is no difference here, hydrogen, carbon, carbon, this is the same way as hydrogen, carbon, carbon. Okay. But the next carbon, now you have to go to the next carbon. So, next carbon, if you see, this is carbon attached to a carbon, then two hydrogens. But what about this one? This one is attached to hydrogen, hydrogen, hydrogen. What about this one? You have to check everywhere. This one is attached also to hydrogen, hydrogen, hydrogen. So, now you see there is a difference here, because this carbon is attached to a carbon, whereas this carbon or that carbon is not attached to a carbon, it is attached to only hydrogens. So, which one wins over the which one wins is here, that means this has got higher priority over this. Okay. We can talk about the triple bonds also, the same case that what is going on with the double bond, the same case is with the triple bond. So, if you have CH versus you are comparing with tertiary butyl, suppose CH3, CH3, CH3. So, what is done? As I said, now you have to see this, view this as a carbon attached with a single carbon, because there are triple bonds. So, you break both the bonds, make it a single bond, but while doing so, as you have broken two bonds, so now this carbon will be regarded as having two ghost carbon atoms. Okay. You can write 0 as you wish, and you can have to do the same thing, a ghost carbon atom at both the carbons. Okay. And here there is no ghost, because it is just normally attached. So, this is your stereogenic center and this is your CH3, CH3, CH3. So, now what will happen? Now, you have this you check what is where is the difference. The first is that this carbon is attached to 3 carbon atoms. So, there is virtually no difference. This carbon is also attached to 3 carbon atoms, but the next carbon whichever you take is attached to only hydrogen, 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 and here they are attached to carbon, carbon, hydrogen. Okay. So, ultimately acetylene wins over T-butyl. So, we can write CH double bond CH2 has higher preference than CH, CH3, CH3. Acetylene has higher preference over tertiary butyl. Okay. So, in many cases you have to do this addition of ghost atoms, like in aldehyde there is the same thing, that if you have an aldehyde versus, so this is your stereogenic center versus COH, a carbon bearing 2 OHs, which are usually not there, but electron withdrawing groups can make a carbon forced to have 2 OHs, okay, versus this. Now, here what you have to do? You have to again do the same thing, that there is a, now this is a carbon double bond to oxygen. So, you have broken a bond. So, now you have to have 2 oxygens here, one of them is the phantom atom. For the oxygen it was attached to a carbon by a double bond. So, now you have to put a carbon here. Okay. So, carbon ghost. Now, you compare these two. So, here this carbon is attached to hydrogen, oxygen, oxygen. This carbon is attached also like that, hydrogen, oxygen, oxygen. So, there is no difference, but the next oxygen is attached to a carbon and this next oxygen is attached to a hydrogen. So, this wins over that. So, CHO. So, the rule says CHO greater than CH OH OH. Okay. So, like that I hope you will be able to sort out several things. So, the rule, as I said, the rule is based on first of all atomic number. Once the atomic number issue is gone, if it fails to distinguish between two ligands, then you apply the atomic weight to distinguish between isotopes. And then for double bond systems, triple bond systems, you consider as if there is a single bond between the two atoms, but in addition these two atoms are attached to what are called ghost atoms. So, you have to duplicate it or triplicated the system. Like in double bond, the carbon double bond is thought to be attached to the normal carbon and you have to duplicate to add another carbon. Okay. So, that is the that is what is the Contd-Prelog rules, okay, about the double bonds. Sometimes what happens that there is a double bond here which is in the cis conformation and there is a double bond here which is in the trans conformation. Suppose this is in the cis. If it is in the cis, that means this hydrogen is on this side, this hydrogen is on this side, methyl is on this side, that is cis. And if it is trans, that means this hydrogen is on this side, this hydrogen is on that side, sorry, this hydrogen, now you have to make trans. So, this hydrogen is here, this methyl is there. Okay. So, in this case, this is your trans. Later on, I think you have already known that this is what is called a Z. Cis is called a Z isomer in absolute configuration, similar to RS nomenclature, and trans is called the E isomer. Okay. So, here the rule is cis precedes trans. That means, between these two groups, this one will be having higher priority. If it is 1, then this is true. Okay. Cis precedes trans, or you can say Z precedes E. Okay. So, same thing, cis precedes trans, Z precedes E. On the same token, if you have groups which are chiral here, a carbon which is chiral and which is having R configuration suppose, and on this ligand you have the same group, but in the S configuration. Okay. If that be the case, then also see atomic number, atomic weight, nothing can distinguish between these groups, only the absolute configurations are different. So, here the rule is that R precedes means R is favored over S, R precedes S. Okay. So, that is this is the rule. So, if you face this type of situation, then you can do that. Okay. I can give you just to end up, I can do one problem where this RS is involved. So, let us do a problem on these sub rules. Cis precedes trans or Z precedes E and then R precedes S. Okay. So, if we draw a molecule which has got a 5 carbon molecule, suppose this OH is to the right, see there is a trihydroxy compound, then you have OH and you have OH here, okay, H. Now, there are 3 carbon atoms and 3 carbon atoms, this is definitely stereogenic, this is stereogenic, and this we are not very sure whether it is stereogenic or not, because that will be depending on the configuration of this and configuration of this. This will become stereogenic when the configuration of this is not the same as the configuration of this stereogenic center, then it becomes stereogenic. If they become same, suppose this is R, that is R, or that is S, that is S, then this carbon is not stereogenic. So, this type of carbon is actually called pseudo chiral center or pseudo stereogenic centers. Okay. Sometimes stereogenic, sometimes not. So, let us see what is the status of this. Now, first you have to assign the RS configuration of this carbon. So, if this is 1, that is 2, that is 3 and that is 4. So, it will be 1, 2, 3, looks like anti-clockwise, but since the hydrogen is in the horizontal side and that means it is towards you. So, actually you have to see behind the board, and if you look at from behind the board. So, this should be in the clockwise direction. So, whatever you see here you just reverse it. So, actually this will be in the R configuration, okay, because the hydrogen is towards you. So, whatever you see, again I repeat, you change it to the other direction. So, what about this one? This is number 1, that is number 2, this is number 3 and this is number 4. The same thing, hydrogen is in the horizontal position. So, you have to be careful. So, this shows that this is looks like R configuration clockwise, but you have to see from the back side, and from the back side it will look like just the opposite. So, it is in the S configuration. So, this is S and that is R. So, now this carbon has become a stereogenic center, because it is now attached with 4 different groups. Okay. The difference here is basically different atoms, and here the difference is because the different configuration of the chiral centers attached to it. Okay. Now, what is the configuration of this? Now, this is the carbon where this group is R and that group is S. So, if you now do the priority sequence, maybe I can just do it here, because that figure looks complicated now or cumbersome. So, this is R, which is on the right, this is CO2H. So, if it is, and this is in the S configuration, which is on the right and H is on the left, CO2H, and this is OH, this is H and that is OH. So, now what is the configuration of this? This will be your number 1, that is the highest atomic number, then comes either this or that, but since R precedes S, R gets preference over S. So, this will be 2 and that will be 3 and the hydrogen will be 4. So, 1, 2, 3 looks like R, but because the hydrogen is on the horizontal side. So, the configuration is S. Okay. So, this is a R S S compound. Interestingly, if you change this weight into this side, so what will happen now? So, this will become also R, because you have remembered in Fisher projection, if you interchange the position of 2 groups, then the configuration gets inverted. So, this becomes also R. So, now this loses its stereogenicity, it is no longer stereogenic, because this is attached to the same, attached to the chiral center, same chiral center with same configuration. Okay. So, you have to be careful. So, this is what is, as I said, that it is sometimes chiral, sometimes not chiral. So, this is called pseudo chiral center. Some books prefer to write small r or small s for this to distinguish between the normal stereo center versus this type of pseudo stereo center. They write small s, small r notation they use. Okay. So, we have now gone through this absolute configuration, the Kahn-Ingold-Prelog system, and you have seen that how to assign the RS nomenclature into a compound which is written in a 3-dimensional formula or in a Fisher projection formula, and there are certain rules. You always remember those rules. And then just one more thing is left, and that is sometimes there are compounds where the 4th ligand is a lone pair. So, if like nitrogen, if the 4th ligand is a lone pair, then because the lone pair has no atomic number, it is only electrons. So, lone pair takes the least, lone pair is the least prior group, followed by hydrogen and then followed by your carbon, then nitrogen, then fluorine, oxygen, then fluorine. Sorry, it is the other way around, less. So, this is less preferred and oxygen is less preferred than fluorine. So, this is the priority. So, always if there is a lone pair, so you have to take into account of the lone pair as the 4th group, and that is the group of least priority, because it has no atomic number. Okay. So, lone pair less than H, less than carbon, less than nitrogen, less than oxygen, less than fluorine. Okay. Thank you.